What connects these seemingly disparate forces that shape our universe? From the everyday light that illuminates your world to the subtle processes that make atoms unstable, it all appears to follow very different rules.
It really does seem that way on the surface.
Exactly. So today, we're taking a deep dive into the profound insights of Nobel laureate Steven Weinberg. Our mission, really, is to unpack his groundbreaking 1979 Nobel lecture.
Right, the one titled Conceptual Foundations of the Unified Theory of Weak and Electromagnetic Interactions. A bit of a mouthful, but incredibly important.
It is. We want to discover how he brought together some of the most, puzzling pieces of the cosmic puzzle.
And at the core of this deep dive, you'll join a journey through two major conceptual challenges in theoretical physics. It's fascinating stuff.
Why?
Well, first, there's the incredibly difficult, sometimes Weinberg called it painfully difficult, understanding of what symmetry really means in physics, especially this idea of broken symmetry.
Okay, broken symmetry. Got it.
And second, we'll grapple with that long-standing problem of infinities that just plagued early quantum field theories. A real headache for physicists.
Right. Infinities sound bad.
They were. But what's truly remarkable, and this is the key, is how Weinberg's work masterfully wove these two seemingly separate threads together into a single, unified understanding of two of nature's fundamental forces.
Wow. Okay, before we get into the lecture itself, maybe we should just briefly sketch the architect here. Steven Weinberg.
Good idea. Just a quick look. Born in 1933, and apparently he was drawn to theoretical physics from a really young age, like 15 or 16.
Impressive. He studied at Cornell, then got his PhD from Princeton in 1957. And his early research years sound quite diverse, moving around, often teaching himself new areas as he went. Places like Columbia, Berkeley.
Yeah, his intellectual curiosity was immense. He even developed a keen interest in astrophysics around 61, 62. That led to his big book, Gravitation and Cosmology, which is still a classic.
Oh, I know that one.
Right. But the pivotal shift, the one leading to the Nobel, happened when he moved to MIT in 1967. That's where his ideas on symmetry, current algebra, renormalization, all these things we'll talk about really came together.
And that led to the unification of weak and electromagnetic interactions.
Exactly, which earned him the Nobel Prize in Physics in 1979, shared with Salam and Glashow. He passed away just recently in 2021, leaving this just incredible legacy.
Okay, so let's dive into that journey of symmetry, just as Weinberg laid it out. It seems the idea first got serious traction in physics back in 1905 with Einstein, right? Relativity.
Yes, precisely. Einstein's work showed that the laws of physics look the same regardless of your motion through spacetime. Constant velocity, anyway.
And this set a powerful precedent, didn't it? Symmetries were seen as fundamental, these sort of a priori principles expressing nature's simplicity.
That was the hope, the ideal. But this initial elegance quickly hit some snags, frustrating ones.
How so?
Well, in the 1930s, physicists had what Weinberg called that painfully difficult realization. There are other kinds of symmetries, internal symmetries, related to properties within particles, not spacetime at all.
Like what?
Isospin conservation is a good example. It seemed to apply only to the strong nuclear force, the one holding nuclei together, not universally.
So already the simple picture was getting complicated.
Very complicated. And it got worse in the 50s and early 60s. You had discoveries like strangeness, another particle property which wasn't conserved by the weak force. And then the big shock, parity violation.
Parity. That's the left-right symmetry thing.
Yeah, the idea that nature shouldn't prefer left over right, but the weak force does. It violates parity. Then came the eightfold way, a particle classification scheme that wasn't even an exact symmetry of the strong force.
So it just looked like a mess. Different forces, different rules, different symmetries, none of them perfect.
Pretty much. It seemed like physics was moving away from unity, not towards it. A real puzzle.
Okay, but you mentioned a crucial distinction earlier. These were global symmetries, right?
Yes, applying the same everywhere. But there was another, more powerful type known. Local, or gauge symmetries.
And quantum electrodynamics, QED, our theory of light and electricity, that was the prime example from the 1920s.
Exactly. And the beauty of a local symmetry, a gauge symmetry, is that it doesn't just describe, it demands things. It requires the existence of mediating particles. For QED, it mandated a massless mediator.
Which is the photon, the particle of light.
The photon, precisely. Massless.
So did people try to apply this gauge idea elsewhere?
Oh, yes. Yang and Mills back in 1954 extended this gauge theory idea, trying to apply it to the strong interactions using a mathematical group called SU2.
Okay. Did it work?
Well, there was a huge problem. Gauge invariance, this powerful local symmetry, seem to always require massless mediating particles, like the photon in QED.
But the strong force isn't mediated by massless particles. We know that.
Right. It's a short-range force, employing massive mediators. So this left this deep, nagging question, as Weinberg put it. Is nature only approximately simple? Were these beautiful gauge symmetries just approximate? Not truly fundamental.
This is where it gets really interesting, isn't it? The idea of broken symmetry. Weinberg said he fell in love with it around 1960-61.
He did. It was an idea migrating from condensed matter physics, the study of solids and liquids.
How does it work, basically?
The core idea is surprisingly elegant. You imagine the underlying laws, the fundamental theory, possessing perfect symmetry. Think of, say, a perfectly round dinner plate.
Okay.
But the actual state of the system, the physical world we observe, especially the vacuum, the lowest energy state, doesn't necessarily reflect that perfect symmetry. Maybe the plate has a single crumb sitting off-center.
Ah, so the lowest energy state chooses a direction, even if the underlying laws don't care about direction.
Exactly. The symmetry is still there in the equations, but it's spontaneously broken in the outcome. In the ground state, it's hidden from plain view.
Clever. But you mentioned a snag earlier.
Right. There was a theorem by Jeffrey Goldstone. It showed that if you spontaneously break a continuous symmetry one with infinite possibilities, like rotating that plate, you must generate a massless spin-zero particle, a Goldstone boson.
And that was a problem.
It was discouraging, yeah, because experimentally, nobody had found any new massless particles floating around that could be these Goldstone bosons. It seemed like the idea, however beautiful, didn't match reality.
I heard Weinberg wanted to quote King Lear in his paper about it. Nothing will come of nothing. Speak again.
He did. Apparently, his editors talked him out of it. Probably wise.
Probably. So how did they get around this Goldstone problem?
This is the crucial twist. Peter Higgs, Robert Brout, Francois Engler, Gerald Guralnik, C.R. Hagen, and Tom Kibble. Several people pointed out a key exception around the same time.
An exception.
Yes. If the symmetry being broken is not just any symmetry, but specifically a local gauge symmetry like the one in QED, then something different happens.
No Goldstone boson.
Exactly. The would-be Goldstone bosons don't appear as independent physical particles. Instead, they essentially get, well, eaten by the gauge mediating particles.
Eaten.
That's a way to think about it. The degrees of freedom corresponding to the Goldstone bosons become the longitudinal polarization states of the gauge bosons, giving them mass.
Whoa. So the gauge particle becomes massive, and the Goldstone boson disappears from view.
Precisely. It sounds like a technicality, and maybe it was seen that way initially.
But it turned out to be more than that.
Much more. There were hints emerging elsewhere, too. Around 1964, the Adler-Weisberger sum rules provided this sort of tantalizing connection between weak decays and strong interaction physics.
How so?
Well, one interpretation involved the pion, a particle involved in strong interactions, acting as an approximate Goldstone boson of a broken symmetry in the strong force itself. It suggested this deep, perhaps hidden link between weak and strong forces. The picture was still fuzzy, but the hints were there.
Okay, so we have this evolving story of symmetry getting more complex, then finding this potential loophole with broken gauge symmetries. What about the other big problem you mentioned? The infinities.
Right, the second major conceptual hurdle. This goes back even further to around 1930. Physicists like Oppenheimer and Waller independently realized that when you tried to calculate quantum corrections beyond the very simplest level in quantum field theory,
You got nonsense.
infinite answers, total nonsense. Imagine calculating the energy shift of an electron and getting infinity. It was, as Oppenheimer later called it, a disaster. It led to widespread pessimism about quantum field theory itself. Many thought it was fundamentally flawed.
But they found a way around it, eventually.
Yes, after World War II. A truly brilliant generation, Feynman, Schwinger, Tamanaga, Dyson, developed this technique called renormalization.
Okay, what does that do? How do you just get rid of infinities?
It's subtle. It's not just throwing them away. The idea is that the parameters you initially write down in your theory, like the bare mass or bare charge of an electron, aren't what you actually measure.
Why not?
Because a real electron is constantly interacting with the quantum vacuum, surrounded by a cloud of virtual particles popping in and out of existence. Renormalization provides a systematic way to absorb the infinities into a redefinition of these physical quantities, the mass and charge you actually observe in experiments.
So you redefine your starting point to match reality, and the infinities get packaged away.
That's the essence of it. You express everything in terms of the measured physical values. And when you do this for QED, the theory of electrons and photons,
It worked.
it works spectacularly. The agreement between renormalized QED calculations and experimental measurements became, and still is, astonishingly precise, like accuracy to 10 decimal places or more.
Wow. But I imagine there was still debate. Was this just a mathematical trick hiding the problem?
Absolutely. Some physicists remained deeply skeptical. Dirac, for example, famously disliked renormalization, but others, like Weinberg, saw it differently.
How did Weinberg see it?
He thought it was wonderful, actually. Not the infinities themselves, but the fact that very few quantum field theories are renormalizable at all. Most theories, if you try this procedure, just don't work. You can't consistently absorb all the infinities.
So the fact that it only works for specific types of theories is actually a clue.
Exactly. For Weinberg, renormalizability wasn't a nuisance. It was a powerful constraint, a guiding principle. It drastically limited the types of theories you could even consider, pointing, he hoped, toward the one true theory. He even worked on renormalization theory for his PhD.
So he was comfortable with it early on.
Yes, but applying it successfully, particularly to the weak interactions, remained a huge unsolved problem for decades. Fermi's original theory of weak interactions and its modifications were stubbornly non-renormalizable. You couldn't use the QED trick.
So QED worked beautifully, but the weak force was still stuck in this non-renormalizable mess.
Pretty much. That lingering doubt persisted through the 50s and 60s.
Okay, this sets the stage perfectly for Weinberg's big aha moment. Fall of 1967, driving to MIT.
That's the story. The realization just hit him. He'd been thinking about applying spontaneous symmetry breaking using gauge theories, but he suddenly realized he was applying the right ideas to the wrong problem.
What was the wrong problem?
He'd been trying to associate the massless gauge boson in some models with particles like remescent from strong interactions, but then it clicked. The massless gauge boson he knew existed was the photon,
Of course.
and its partner in a unified picture shouldn't be another strongly interacting particle, but the mediator of the weak force, the massive intermediate vector boson that people had suspected for years.
So unify weak and electromagnetic forces using a gauge theory,
An exact gauge theory.
but one that is spontaneously broken.
Precisely. The underlying symmetry is perfect, linking electromagnetism and the weak force. But the vacuum state breaks it, giving mass to the weak mediators, W and Z bosons, while leaving the photon massless.
And crucially, because it's a gauge theory.
It should be renormalizable, just like QED. Suddenly, all the pieces fit together. Broken symmetry provides the masses. Gauge invariance provides the renormalizability.
That's elegant. Did he have a specific model?
He did. In that 1967 paper, he proposed a specific model based on a symmetry group called SU2XU1, applied initially just to leptons like electrons and neutrinos.
SU2XU1.
This model predicted not just the existence, but also the approximate masses of the charged W bosons and the neutral Z boson, based on the known strength of weak and electromagnetic interactions and one new parameter, the Weinberg angle. And it kept the photon massless, naturally.
And the key was that symmetry and renormalizability dictated almost everything.
That was the beauty of it. As Weinberg said, all details of the theory are completely determined by symmetry principles and renormalizability, apart from a few fundamental constants you have to measure. It wasn't just arbitrary model building.
And Abdus Salam came up with something very similar around the same time.
Independently, yes, in 1968, which really underscores how ripe the idea was, how natural it felt once the pieces were in place.
But, okay, having the idea is one thing. Proving it actually is renormalizable, that sounds like a massive task. Did Weinberg prove it right away?
He didn't, actually. He struggled with it. The way gauge theories were typically handled back then, using the standard mathematical formalisms, made proving renormalizability extremely difficult, especially with spontaneous symmetry breaking involved. It wasn't obvious how to show all the infinities canceled correctly.
So who cracked it?
The big breakthrough came in 1971 from a young Dutch physicist, Gerard 't Hooft. He published this just beautiful paper, as Weinberg called it.
What did Hooft do?
He employed a different way of setting up the calculations, using a particular type of gauge, mathematical choice, that made the underlying cancellations and the renormalizability much clearer. It showed that these spontaneously broken gauge theories were indeed consistent and calculable.
Ah, so 't Hooft provided the key mathematical tool.
He provided the crucial insight and demonstration. The proofs were then formalized and completed by others, like Benjamin Lee and Jean Justin, soon after. But Hooft's work was the turning point that convinced the community the theory was mathematically sound.
Okay, theory sound. What about experiments? You need proof. What was the crucial test?
The smoking gun was the prediction of neutral current weak interactions.
Neutral currents.
Right. Standard weak interactions involved charge exchange, mediated by the charged W bosons, like a neutron turning into a proton. But Weinberg's theory required a neutral mediator, the Z boson, which would cause weak interactions where charge doesn't change hands. For example, a neutrino could scatter off a proton without changing into a muon, just bouncing off via the Z.
Had people look for those before?
There had been speculations and searches going back decades, but the results were ambiguous or negative. But Weinberg's theory didn't just allow neutral currents, it made a definite quantitative prediction for how strong they should be related to that Weinberg angle.
So it was a make-or-break prediction.
Absolutely. And Weinberg himself looked into the experimental situation in late 1971. He realized something interesting.
What was that?
Previous experiments had set upper limits on neutral current processes that were actually quite low, leading some to think they just didn't exist. But Weinberg calculated the rates predicted by his theory and found they were just low enough to have plausibly escaped clear detection so far.
So close to the existing limits, but maybe just under.
Exactly. For instance, the ratio of neutral current to charged current neutrino scattering off protons, he predicted something like 0.15 to 0.25. The experimental upper bound at the time was about 0.12, 9, and 0.06. Very close.
That must have been encouraging, like, look harder.
That was precisely the conclusion. Every reason to look a little harder. And they did.
And success.
In 1973, the Gargamel bubble chamber experiment at CERN announced the striking discovery of neutral currents. Clear events showing neutrinos scattering without changing charge.
Wow, that must have been huge news.
It was enormous, quickly confirmed by experiments at Fermilab and elsewhere. And over the following years, measurements of neutral current processes with steadily improving precision consistently matched the predictions of the Weinberg-Salam model. It was a triumph.
A direct confirmation of the theory.
Yes, although it's interesting, Weinberg later said that even if the specific SU2IU1 model turned out to be slightly wrong in its details, the truly important thing for him was the validation of the core idea that weak and electromagnetic interactions arise from an exact but spontaneously broken gauge symmetry, making them renormalizable. That underlying principle felt right to him.
That search for the underlying principle, it makes sense. Did this success impact how physicists thought about the strong force, too?
Oh, absolutely. The early 70s were just a revolutionary period. Around the same time neutral currents were discovered, in 1973 came another huge theoretical breakthrough, asymptotic freedom.
Asymptotic freedom sounds intriguing.
Discovered by David Pulitzer and independently by David Gross and Frank Wilczek. They found that in certain types of gauge theory specifically, the kind needed for the strong force, called non-abelian gauge theories, the interaction strength actually decreases at very high energies or short distances.
Wait, the strong force gets weaker up close? That seems backwards.
It does, but it explains why quarks inside protons and neutrons behave almost like free particles when probed at high energy. And Weinberg, along with Gross and Wilczek again, quickly realized the implications.
Which were?
If you built a gauge theory of the strong force, which became quantum chromodynamics or QCD, you didn't need spontaneous symmetry breaking for it. The gauge symmetry could remain unbroken. The mediating particles, the gluons, could be massless.
So, unlike the weak force, the strong force symmetry isn't broken.
Right. And asymptotic freedom had a flip side. If the force gets weaker at short distances, it gets stronger at larger distances. This explained confinement, why you never see isolated quarks or gluons. The force holding them together becomes incredibly strong as you try to pull them apart.
Okay, so QCD emerges as the theory of the strong force, based on an unbroken gauge symmetry.
Exactly. And here's another beautiful consequence Weinberg highlighted. Remember all those approximate symmetries of the strong force, like isospin, strangeness conservation, parity conservation, charge conjugation?
The ones were causing confusion earlier.
Yes. It turns out, once you write down the simplest possible gauge-invariant, renormalizable Lagrangian for QCD, those symmetries pop out automatically, almost for free.
You don't have to put them in by hand.
No. The constraints of gauge invariance and renormalizability are so powerful, they basically force the theory to respect these symmetries, at least to a very high degree. It was an astonishing unification of concepts.
So that whole confusing pattern from the 50s and 60s.
Was suddenly explained. As Weinberg put it, the pattern of approximate symmetries wasn't fundamental. It was a simple consequence of the underlying exact gauge symmetries of the standard model, electroweak plus strong forces, combined with renormalizability.
It flipped the perspective entirely.
Completely. Internal symmetry is now at the point where space-time symmetry was in Einstein's day. His point was profound. Maybe the only true symmetries are the exact gauge symmetries that govern all interactions. The apparent approximate symmetries are just low-energy artifacts.
Incredible. So with the strong and electroweak forces described by gauge theories, what are the big remaining questions? Where does this path lead next?
Well, one huge question revolves around those Higgs bosons, the particles responsible for breaking the electroweak symmetry. Are they truly elementary, fundamental particles as described in the simplest version of the standard model?
Or could they be composite, made of something else?
Exactly. If they're elementary, we should find just the specific Higgs bosons predicted. If they're composite, it implies some new, incredibly strong, extra strong, or technicolor force binding their constituents together and potentially whole new families of particles interacting via this force. The LHC experiments are probing this, but the nature of the Higgs sector is still a major area of research.
And the elephant in the room. Gravity. How does that fit in? Still resistant to this quantum field theory approach.
Still the toughest nut to crack, yes. Gravity, as described by general relativity, is notoriously difficult to quantize in a renormalizable way using standard QFT techniques.
Why might that be? Weinberg had an idea, right?
He suggested it might be about energy scales. Gravity is incredibly weak compared to the other forces at everyday energies, but calculations suggest that at an extraordinarily high energy, the Planck energy around 1019 GeV gravity would become comparable in strength to the other forces.
So maybe our current theories are just low-energy approximations, effective field theories.
That's the idea. Perhaps at the energies we can access, we only see the renormalizable interactions because any non-renormalizable interactions, like quantum gravity effects might be, are suppressed by powers of this huge Planck energy scale. They're just too weak to easily detect.
Which makes gravity seem unique, almost the only super weak interaction we could have noticed.
Plausibly, yes, it's an intriguing perspective.
What about fundamental conservation laws? Like protons not decaying or lepton number being conserved. Are those truly absolute?
Weinberg raised doubts here, too. He pointed out that within the standard model's gauge symmetries, these conservation laws, baryon number for protons, neutrons, lepton number for electrons, neutrinos, arise automatically. They're accidental symmetries, consequences of the gauge structure, and renormalizability.
So they might not be fundamental principles themselves.
They might not be. If we ever observed protons decaying, however rarely, or found definitive evidence for neutrino masses, which implies lepton number violation, it would be strong evidence against baryon and lepton number being fundamental laws. It would bolster the view that the only truly fundamental internal symmetries are the gauge symmetries themselves.
Which points towards perhaps an even deeper unification.
Exactly. This leads to the idea of grand unification, or GUTs, proposed around 1974 by Howard Georgi and Sheldon Glashow, and also Georgi, Helen Quinn, and Weinberg.
What's the core idea of GUTs?
The idea is that the strong and electroweak forces, which have different strengths at low energies, actually become equal in strength. They unify into a single force, described by a larger gauge group at some incredibly high energy scale, perhaps around 1016 GeV.
Close to that Planck scale again.
Remarkably close. Asymptotic freedom is key here. The strong force gets weaker at high energies, allowing it to meet the electroweak forces, which get slightly stronger.
Do these GUTs make testable predictions?
They do. One of the most dramatic is proton decay, though the predicted lifetime is incredibly long, maybe 1032 years or more. Experiments have looked hard but haven't seen it yet, pushing the limits on the simplest GUT models. They also predict relationships between particle masses and, significantly, a specific value for the Weinberg angle, which actually matches experimental measurements quite well.
So tantalizing hints, but still pieces missing, like why the particles have the specific masses they do, or why those Higgs scalars exist.
Precisely. Explaining the pattern of quark and lepton masses, the mixing angles, the existence and properties of the Higgs, these remain major open questions, perhaps pointing towards physics beyond even grand unification, maybe involving supersymmetry or string theory.
Yet, even with these open questions, Weinberg seemed optimistic about the path forward.
He did. He spoke about the stubbornness of quantum field theory, how its internal consistency, especially renormalizability, severely restricts the possibility. It doesn't let you build just any theory. It forces you down specific paths.
And he used that beautiful Plato's cave analogy.
Yes, it's powerful. We're like prisoners in a cave, only seeing shadows on the wall. These shadows are the low-energy phenomena we observe, where the fundamental symmetries are spontaneously broken and hidden. Nature looks complicated, maybe even arbitrary down here in the cave.
But by studying the shadows carefully,
By looking long and hard at the shadows, we can deduce the shapes of symmetries. We can infer the properties of the exact underlying principles that govern everything, even though we don't see them directly in their perfect form. We can glimpse the beauty of the world outside the cave.
what an incredible journey we've taken, really, following Weinberg's insights. From that confusing picture of different forces and broken rules to this elegant, unified framework built on gauge symmetry and renormalization.
It truly is amazing, and I think the core takeaway really is just the profound power of demanding these principles: exact gauge symmetry, renormalizability. They act like incredibly sharp razors, cutting away at possibilities and revealing this underlying simplicity and structure in nature.
It makes you wonder, doesn't it? As you navigate the complex systems in your own world, maybe looking for those underlying exact symmetries, those core unbreakable principles, could unlock some unexpected clarity and deeper insights too.